Nuclear reactions are balanced in terms of atomic number and mass number, unlike other chemical reactions, which are balanced in terms of atoms. If it's been a long time since you thought about atomic number and mass number, let me give you a little refresher for this atom that I'm writing down here. 86 is the atomic number, and this is the number of protons in this atom. 222 is the mass number, and the mass number is the sum of the protons and neutrons in this atom. Atomic number is always written in the bottom left-hand corner, and mass number is always written in the upper left-hand corner. When we balance nuclear reactions, the sum of all of the atomic numbers on the left-hand side of the equation will be equal to the sum of the atomic numbers on the right-hand side, and the same for the mass numbers. Their sum will be equal on the left and the right-hand side. So when we're balancing nuclear reactions, we use a lot of different subatomic particles to help us balance the reaction. And I'm going to begin by giving you a list of 5 subatomic particles that you will see and use as you're balancing nuclear reactions. In no particular order, the first one that we are going to look at is the proton. Now you know that the proton is a positively charged particle that's inside the nucleus. There are 2 different ways that we indicate a proton in a nuclear reaction. One is with the lowercase p, which is what we're familiar with seeing. A proton has 1 proton and it has no neutrons, so it has a mass number of 1 and an atomic number of 1. Sometimes we see the proton symbolized with the H, the symbol for hydrogen, because a hydrogen atom has just 1 proton in its nucleus and no neutrons. Another subatomic particle that you're familiar with and that you will see in balancing nuclear reactions is the neutron. The neutron, as you know, has the symbol of lowercase n. There are no protons in a neutron, so the number of protons, the atomic number, is 0. There is 1 neutron, so the mass number, protons plus neutrons, is 1, and there is no other symbol for neutron. We also have the electron. As you know, the symbol for the electron is a lowercase e. Electron has no protons and no neutrons, so it is a mass number of 0. And this is something that's maybe kind of funny. The atomic number for an electron is -1. Just think about it in terms of its charge. The the charge of an electron is opposite that of a proton, so an electron effectively cancels out the presence of a proton by its charge. We can also see the electron symbolized with the Greek letter beta. Still has a mass number of 0, atomic number of 1. This symbol is referred to, occasionally we refer to this as a beta particle. There are 2 other particles that we haven't used before or we haven't encountered before. And the next one that we're going to talk about is the positron. The positron is like the opposite of an electron. So we could symbolize it with the same letter we use for the electron. It has no mass number, but it has a positive charge instead of a negative charge. So it's not the same thing as a proton because it doesn't have a mass number. And we do indicate a +1 down here instead of just saying 1, just to make sure that we're definitely distinguishing it from an electron. That positive sign is important just to make sure there's no confusion. And we could also symbolize a positron with the beta symbol, still using the +1 to make sure that it's very clear that we're talking about a positron, not an electron. And then last but not least, we have what we call an alpha particle. An alpha particle is basically a helium atom, so we will symbolize it with the symbol for helium. It has 2 protons and it has 2 neutrons, so it has a mass number of 4. We will also sometimes see it symbolized with the alpha, mass number of 4, atomic number of 2. So like I said, when we're balancing a nuclear reaction, we're really just wanting to balance it in terms of conserving atomic number and mass number. So this atom right here undergoes what we call radioactive decay, which is just a spontaneous emission of 1 or more of these types of subatomic particle. I can see there that I spelled particle wrong for the alpha particle. I'm going to fix that real quick. Particle. Sometimes it's hard to talk and write at the same time. Now that looks like a D. Alpha particle. Okay, back to this. So this atom undergoes radioactive decay, meaning that it just spontaneously emits subatomic particles. This atom spontaneously emits an alpha particle. And when it emits an alpha particle, it generates or it creates another type of atom. So there's some other type of atom out here that it creates with an atomic number and a mass number. When we're balancing nuclear reactions, we typically have a format kind of like this, and our goal is to figure out what the atom is that's created in this particular reaction. And in order for us to do that, we're going to maintain the conservation of atomic number and mass number. Starting with atomic number, the atomic number is 86 on the left-hand side, and that means our atomic number on the right-hand side also needs to be 86. So that means that this atom that we create needs to have an atomic number of 84, because 2 plus 84 is going to equal 86. Now we're going to do the same thing for the mass number. The mass number has to be conserved. We're starting with 222. So over on the right-hand side, we need a mass number over here of 218, because 4 plus 218 is going to equal 222. Our last task is to come up with the identity of this atom. What is this atom? To figure this out, we're going to use the atomic number, 84, and we're going to go to the periodic table. We're going to find the atom that has atomic number 84 on the periodic table, and we'll see that it is polonium, PO. So again, our strategy here is to begin by figuring out what the atomic number is, use the atomic number to figure out the identity of the atom, and then also fill in the mass number at some point along the way.